It's like in exactly. Yeah, it's like and the maker thing. It's like his first semester.
Yep. Start. Yep. Give it a go.
Hey, my name is Kevin. I'm here to talk to you guys about the Computer Science Club. We meet on Tuesdays and Thursdays between 12 and 3 p.m. We're in the computer lab over here in the liberal arts building. It's 152, and it's section D. So you go inside the computer lab. There's another room on the left side when you walk in, and that's where we meet. This semester, we're working on a couple projects. We're going to be doing something with Schuster, Professor Schuster, for the engineering club. He is looking for programmers to write C code to generate G code for the 3D printers. So if anyone's ever been interested in how that works, it's a great way to find out. We have access to some Arduino boards, a Raspberry Pi server that someone's trying to build this semester. He's also looking for help with that. We basically just hang out, do homework, talk, and work on these projects. So feel free to stop by anytime between 12 and 3. Does anybody have any questions? All right, well, hopefully I'll see some of you there. All right.
Okay. Thank you, Kevin.
Thank you. Have a good day.
All right. Okay. What Kevin did not mention is, after I step out of the lab, people would also talk about professors. Like, if you're planning to take a class, the following semester, they would start to talk about, oh, don't take it from blah, 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 and stuff like that. Unfortunately, I'm not avoidable because I'm the only one teaching 440 and 310. So it is like, not really avoidable, in that case. So they can talk all about it, but in the end, you still have to go take that class. Unless you go to a different college, like Sac City. You can take it over at Sac City. But we do have 3 people from Sac City over here today, this semester. But Kevin was right that we are trying to hook up with the engineering club, where they have a lot of interesting projects. The engineering club is not really quite what the name implies, because when people think about engineering, they think about kind of boring stuff like drafting, all the calculation of forces and whatnot, right? That's not what it is. Let me give you an idea of what the engineering club is planning to do this semester. So let me go to my shared folder and look up the folder that he sent to me. Okay, so we are looking into spring projects. So they got all of these projects, that they want to do sometime in this semester. So they have this aerial mapping drone program thing. So somebody wanted to use a drone to carry a camera to fly around on campus. And you guys would say, well, there's nothing really innovative about that, because that's what drones do, right? Well, they want to fly the drones at about eye level, so the drone is going to see, or the camera will see what a normal person walking around would see, and then it would take all the data points from the camera footage and try to come up with the right name here. I think it's called a point cloud. So they can 3D model out of the 2D images of the camera. And then they can reverse engineer, the buildings and whatnot, and texture map everything. So that's kind of what the drone project is about. I kept telling them, use a kind of wheel-based robot that's going to be safer, because when you have a drone that's flying at about eye level, that's kind of not very safe. It's kind of like a lawnmower.
Yeah.
Yeah.
I mean, they're also pretty controversial right now in terms of if they should even be flying in public spaces.
Yep. So I would just, use one of those accessibility, how do you call those, scooters? Okay, put a fake, person in it, and then mount the camera on top of that, and just, drive that thing around a few times. It's a lot safer, people won't notice, right? So that's one thing that's kind of interesting. This is interesting. It's called diesel stiller, and with a typo too. Okay, I can fix that. Okay, so diesel stiller is interesting. Let me see if I can find the actual document of describing what it is. So here's the proposal. Does it have any pictures?
Is it from the student center now?
Yeah. Yep. So they're gonna put this thing. Okay. Do we have a larger picture? No, we don't want it. Okay. So this is Diesel Ziller. I think it is, the footprint is about 10 by 18 feet or something like that. It's not that big, okay? So they're gonna put this in the state fair. And they're inviting high schools around the Sacramento area. And I think at this point there are 4 unified school districts and about 14 high schools that have expressed interest in duking it out with Diesel Ziller. So what they're going to do is they will mount special sensors into the mouth of Diesel Ziller. So when a drone flies by and aim and then shoot a laser beam, Diesel Ziller will keep count of how much it has got hit. So now you have a swarm of drones remotely controlled by people versus Diesel Ziller in this year's state fair. So that's one of the other things they are planning to do. Now, of course, in computer science, what we're interested in is automating those drones. So they won't be automated, they won't be remotely controlled anymore. They will be automated. So that will be kind of really cool. But we can also get into trouble for doing that sort of thing. Because Homeland Security may look at that and go like, this is not, it's not looking good. So that's one of the other projects. And let's see, what else?
What's the 3D? What is the 3D?
Which one?
This
This one? Okay, this one is an empty folder, but I can tell you about it. So what they want to do is to make a rig so that there's a rotating platform and also a actuation arm. So on the rotating platform, you can put a vase or something to be scanned. And then the camera, which is just a normal 2-dimensional normal video camera, would continuously take pictures of the thing that is being slowly rotated. And then they will collect all the point cloud, all the images and identify features and whatnot, and they will turn the pictures back into a 3D model. In other words, you're making a 3D copier. And this is the 3D scanner to scan an object. So once you can represent the 3D object in 3D points, then you can feed that program into a 3D modeling and a slicer program, and then you can use a 3D printer to print that thing as a copy. So that's basically what the project is about. So there's a lot of really kind of interesting stuff going on with, they have a molecular active site project where a chemistry teacher is trying to visualize a protein structure so that people can actually look into it's going to be constructed in slices, so you can actually open it up and look at what the inside of the protein structure looks like, or protein molecule looks like. So all kinds of fun stuff. So we are trying to hook up with the engineering club. The computer science club is trying to hook up with the engineering club to see if we can lend a hand on things that are computational in nature. And by the way, they also have a BB-8 robot from Star Wars, except the one that they have is remotely controlled. So if they have enough computer science people interested, they might be able to automate BB-8 to do certain things. So that would be kind of cool to have BB-8 to replace the flying drone to kind of scan the campus and get a map of everything. That would be kind of cool.
Yeah.
But I'm an R2-D2 fan. I'm loyal to R2-D2. All right, so that's the club stuff. Okay, if you have any questions, you can ask Kevin. But I am the advisor of the club as well, so I can answer some of those questions. All right, so what we'll do today is to talk about memory access in RAM. So we will learn how to read and write to memory. And we'll also talk about register bank, which is a major component inside a processor. Okay, and then on Thursday, we'll start to put things together. Okay, we'll basically try to look into, okay, so now we have the ALU responsible to do all the calculations. We have all the registers to store the values after computation, to supply values to be computed. And then we have RAM to store the results, and also to supply instructions. So now the big question is, how do we execute instructions? your music box assignment is due on Thursday, which is exactly the right time to finish that project, to finish that assignment, because then we can use the music box, what we learned from the music box, to directly apply it to one key component of a processor, which is the microcode engine of a processor. So that's kind of a preview of what we'll be talking about. So before we get to there, let's go ahead and take a look at RAM. So once again, I want to show you where to find the documentation of that. So you can go to memory library and just look up RAM. Okay, so this is the basic description of RAM. And whoever wrote this software actually spent quite a good bit of time to explain how the components work. So we'll be doing experiments with this component today. It's not going to be a homework assignment. I will be using LogicSim to demonstrate how to use a RAM module. All right, so let's go ahead and do it. So now we pick out a RAM module and put it here. So the first thing we do after we pick up a module or pick up a component is we look at the properties. Notice it's got 3 properties. The first one is address bit width, which you already know because you need to know that for your music box homework assignment. So the address bit width is controlling how many bits do we have on the address port, which is this one over here. The address port is used to specify a location. In this case, because it is a RAM module, that location can be used for read or write operation, and not just read operation in a ROM. So that's the A port, which is the address port. And then we also have a data port here, which is basically the same thing as in a ROM module. It controls the width of the data port, which is also controlling, how wide is each location in the RAM. So each of these locations, in this case, is 8-bit wide. We can change that to something else, okay? And then the last one is data interface, and we got 3 options here. The first one is one synchronous, the next one is one asynchronous, and then the last one is separate load and, okay, let me see if I can, separate load and store ports. So what we are going to pick is the first one, which is synchronous load store port. Load store is kind of an older name to mean read write. So it allows us to specify, are we reading from RAM or are we writing to RAM? Okay. Load is reading and store is writing. Everything is seen from the perspective of the processor and not from the RAM module itself. All right. So now that we have a RAM module put here, let's go ahead and see whether we can specify a location, put a content into it, and then read back some content. So the way to do this is we will end up specifying a whole bunch of ports. This is going to go to my address port. So the pin itself has to be 8-bit wide to match the width of the address port. So this is cell or select. It has exactly the same meaning as in the ROM, which basically means if this pin is a 0, the RAM module is not selected. It does not pay attention to all of the other ports. If this pin is a 1, it means this particular RAM module is in fact selected, and it will pay attention to the other signals. So we'll use another input pin to control cell or select. In real world, the select pin is usually active low. In other words, it is usually starts with a slash, which basically means a 0 means it is selected, and a 1 means it is not selected. But LogicSim is fairly hardware independent, and that's why it is not active low in this case. The next one is, guess what this one is? It's the clock, exactly. So once again, the RAM module depends on a transition from 0 to 1 in order to write content into memory address locations. So we'll give it another pin that we can toggle manually. This is load, which means if it is 1, it is a read operation. If it is a 0, it is a write operation. So we'll go ahead and connect a pin to that too, so that we can specify the direction of our operation. CLR is the same thing as a 0 in the register, which means if it is a 1, it will unconditionally turn all the content of this particular RAM module into zeros. And it is asynchronous. It is not guarded by the select pin, which means this RAM module may not be selected. There's no rising clock operation. As soon as the clear signal is a 1, the content of this RAM is cleared. Okay? So it doesn't need to be addressed in order to be cleared. So we'll go ahead and test that theory as well. So put one over here. Now the data pin is a little bit tricky to document. So we'll go ahead and hook up an output pin for now. But later on we'll find out that sometimes we actually want to have an input pin because it is bi-directional. Okay. All right, so now we have everything connected to a RAM module. We can start to experiment a little bit, okay? The way it is set up right now is we can read operations, but we can't really quite specify write operations because we can not specify the content here. When you go into simulation mode, you cannot change the state of these individual bits because that's an output pin. Okay, if it's an output pin, you cannot change the state. It is only reflecting what is on the wire, but you cannot change the state. You can change that to an input pin, but then we have a different problem because as an input pin, it is driving those individual wires. So when your RAM, when you try to specify read operation, then the RAM will try to drive the wires, the input pin will try to drive the wires, and if they do not agree, what do we end up with? We'll end up with a fight. Okay, we'll end up with a fight, which is not a good state. So that means we have to kind of be careful about this output. There is a way to solve that problem. So we'll get to that solution when we get to that part. All right, just like with ROM, if you want to, you can inject content into the ROM. And you can go ahead and actually just change one location if you want to. It's a 2-digit hexadecimal number, so we can just type 7F if you want this particular bit pattern, which is 0 followed by 7 zeros, 1 0 followed by 7 ones in that particular byte. Okay? So we want to see if we can read that operation. Well, let's check out the clear first, okay? So right now, it is not selected because the select pin is a 0. And the clock pin is resting at 0. We do not see any transition. And the operation specifier is a load up, LD is a 0, which means, but since select is not a 1, the RAM chip is not really paying attention to anything. If you assert clear, it will still change the content back to 0. Okay, so this confirms what I said a little bit earlier, that a clear signal is not gated. It is not gated by the cell line. Okay, a RAM module doesn't have to be selected in order for the content to be clear. Can anyone think of why that is the case? What is the application of that clear port in a real computer? The reset button, or system-wide reset, okay? So you want to reset RAM content in case somebody pressed the reset button, or in case the watchdog decides, oh, okay, something bad has just happened. Let me just restart the entire system from scratch with a known state, okay? And having your RAM module all zeroed out is a known state, and it is typically considered a safe known state. Yep.
Doesn't RAM lose memory regardless because it's in a volatile memory? So like once this power went up, like
It depends on the kind of RAM, because there are two types of RAM. One is static RAM, and the other one is dynamic RAM. With some types of RAM, when you power up a computer, it can end up with random content in the RAMs. So that would not be good because so you definitely want to hold the reset line, let everything, every single component, including your network cards, your USB hub and whatnot, you want everything to reset to a known state. And then when you start the computer in the firmware, it can at least make certain assumptions about what the other components are at.
oh.
Okay, so that means in order to test this, we have to deassert the clear line because otherwise I cannot make any changes. So let's go ahead and pick out this location, change that to B5, my favorite sci-fi show. You guys are you guys are way too young to remember that. This is like Oh,
They
old
rerun on the
show.
Sci-Fi Channel.
Sorry?
They rerun it on the Sci-Fi Channel.
Oh, they do?
Yeah.
Okay, well, I don't have cable. But I do have all the episodes downloaded, so I don't need cable to watch that. Okay, so B5, okay? B5 is at that location, and I want to read that location right now, okay? So there are several things I need to set up. First, I need to know the address of the location that I want to read from, which is the one that has a B5. What is the location? A is correct. 10 is also correct, because you're specifying the value, but A is specifying the hexadecimal representation of that value, so it is both correct. So it is A, which is in binary. What should I specify as the address? Okay, so 1010 as the least significant byte, because the most significant 4 bits are all zeros, because it is 0A to be more precise. Okay, all right. And then what do we need to do? We need to specify this as a read operation, which means LD needs a 1. There we go. And nothing is happening because the RAM chip is not selected. So what we do now is we now select the RAM chip, and this is the major part. Okay, this is the main part. As soon as you select the RAM chip, it will start to interpret all of the other pins, and now it says, oh, okay, you want to access location 0A, and this is a read operation, and as a result, the RAM chip is driving the D port, which means the D port, the wires coming out of the D port is now being driven by the RAM module to reflect the content of the addressed location. Is that okay? So from this perspective, it is kind of like the raw module in your music box assignment, except with this one, we have this one extra line, or 2 extra lines. One is LD to specify whether it's a read operation or write operation, and then the other one is the clear line, which is used to clear the content of this particular RAM module. Both of these lines do not apply to ROM, because ROM means read only. As a read only memory, there's no clear, okay, because you don't want to clear the content of your ROM. If your BIOS, okay, if the BIOS of your computer is RAM based, what's going to happen when you reset the computer or turn it off? You would have lost your BIOS, right? And without a BIOS, what becomes of your i7 super duper core computer? It becomes a space heater. It will turn on. I mean, it will clock. It will do something. It will heat up the room. That's what it's good for. Okay. So you don't want your BIOS to be in RAM. Okay. At least when you start with the computer. Now, at some point, you do want to move your BIOS into RAM, because the BIOS is sitting in ROM, and ROM are slow devices. Okay, and they're also typically kind of narrow too, which means that they're byte wide instead of 64-bit wide. So executing programs from ROM is very, very slow. Okay, so as soon as you boot up, most computers will now try to load all the ROM content into RAM so they can execute a lot faster. Yep.
So the A pin is the address.
Yes.
The output, that's just B5 hex in binary.
That is B5 in hex in binary, because we have 1011 for the B part, and then we have 0101 for the 5 part.
Okay.
Yep. And you can also you can click on the wire itself. It will also tell you that it is -75, because that's the signed decimal interpretation of the binary bit pattern. Yes.
So, how do you store it without doing it manually? Is that with LD?
Yes, LD is the key to specify the direction. So when LD is a 0 and the RAM is selected, then you're saying, okay, this is a write operation. Now, a write operation is the only one where the clock needs a transition in order for the actual write operation to occur. When you're reading, there's no need for the transition. So the clock signal is not used for read operation, but it is used in the write operation.
So, okay.
Okay?
It'll write from the A side, right?
It will.
From the A side or the...
It will write to the location specified by the A port. So the A port is, remember last time I think we used this notation. D is the result, right? But A is the index into your RAM.
Oh, so right from the D. It'll write from the D port.
It will specify the content of the location at the D port. So this is a read operation. This is a read for LD load operation. If you do it the other way around, RAM bracket A equals D, now it is a write operation or store. Just two names for the same thing. Okay. All right. So now that we know how to perform a read operation, let's see what we need to do to perform a write operation. Okay. So to perform, let me just go ahead and take out all of these things first. So let's say we want to write to a this location over here, which is 0D. Okay. So we want to change this location to the content of, I don't know, 7, 8. Okay. So we want this content to change to 7, 8 in hexadecimal. What are we gonna do? Now, certain things we already know how to do. Okay, we know. Oh, we need to change these pins, don't we? So these pins are output pins, which does not let me specify the content of this wire. So it's easy to change that because we can go to output, specify a no here, and I don't need to use tri-state, so I'm going to turn off 3-state as well. So now I can specify the content here. But when we have this, then we have another problem, because if we want to perform, okay, so let's say that we want to change this to 7, 8, which is what we want. Okay, so this is 7 and that's 8. So now that we have 7, 8 specified here, but if you do not specify the operation correctly, then we have a problem. See the red wire? The red wire means we have a bus fight. A bus fight basically means that one side of a wire is trying to drive it in one direction, and then the other side of the wire is trying to drive it in the opposite direction. So now we have a problem, okay? And if you click on the red wire, it would also explain to you that we have an error. It will tell you the bits that are having errors. In other words, the 1, 1 is consistent. Both sides are trying to drive those particular pins high. So we don't have a problem. The 0 doesn't have a problem either, or bit 1. See that E is 0E? That 0 is also not having a problem because both the RAM module and the input pin are both trying to specify a 0 on that wire. So we don't have a problem. But for all of the other E, quote unquote E bits, it is a report of an error, which is basically saying one side is trying to drive it high, the other side is trying to drive it low, and we have a problem. Okay? And you can also just kind of 1011 is B, and then we have a 5, which is 0101. That's what the RAM is trying to drive the wires. And then the input pin is trying to drive 0111, 1000, and you can see we have a problem here. One is trying to drive high, the other one is trying to drive low. Yes?
What would happen if that was actually like in a circuit?
Okay, we'll answer that question, but in just a little bit. Okay, so these are the bits that are having problems, and those are the ones reported as E when we click on the wire. Question?
Yeah, those numbers don't make sense to me with what's up there. What do you have?
This is a B5 and this is a 7, 8. So the B5 is what is at the content. This is still a read operation. Because LD is a 1, so it's still a read operation.
Okay, so it's looking at the B5, not, I see.
It's looking at both.
It's not looking at the RAM location. It's looking at the value of the B5 and
Correct.
the input value. I got
Correct.
it.
It's not looking at the address, it is looking at the content at that address, which is the B5. And then the other side comes from the input pin, which is a 7, 8. Okay. Yep.
So is input was B5 also, there'd be no error because it lines up?
If the input is also B5, then you would not have the error, correct. So though that particular wire will turn black, which basically is reported as no problem. Okay, so that was the question. Okay, there was a question earlier of, okay, so what actually happens in the electronics when one side is trying to drive high and the other side is trying to drive low? So what I'll do is I'm going to show you the NAND 2 gate here, because we need to kind of look at it from the transistor perspective. So the NAND gate is specified as this. Okay. Okay. So these are the P channel MOSFETs and these are the N channel MOSFETs, right? So we kind of know this. So you can imagine that on one side we have a setup like this, on the other side we have an identical setup. So N channel, P channel over here, and so on. Okay. So we know that with a NAND 2 gate, okay, this wire and this wire are connected. This one and this one are connected. And we know that by itself, it doesn't have any conflicts. In other words, there's no way for current to go from VCC or power supply all the way to ground by itself because of the way we arrange the transistors. So we know by itself it is safe. This one, once again, by itself it is safe because of the way we connect the wires. So no problem. Each one has an output. This is the output tap. This is the output tap. So with the output tap connected, now the question is, what if one is connecting to high? In other words, what if one has one or both of these P channels connected? So this line is actually, let me use a different color so it's visually visible. So what if this line is connected? These transistors are on, so that one side is driving high, and then the other side is driving low because these two transistors are on at the same time. What if we have this scenario? Well, the wire in between has no or close to zero resistance. So now we have current going from here, which is on one side of that picture, the input pin, going across the wire to the RAM module, and then eventually be sunk to ground. Okay, and there is no intentional resistance anywhere within this circuit. In other words, I'm not putting in a 10K ohm resistor here, so that with a 10K ohm resistor, things are not quite as bad, because what's going to happen is the voltage drop is going to be across the 10K ohm resistor. For the most part, you'll have very little current actually passing through the transistors, so there won't be any problem. But without any intentional resistor in here, then we are only relying on the built-in resistance of the transistors to slow down the current. And they tend to be pretty small. Okay, so we have, this is just theory, okay? So let's say we have 10 ohm resistor here, 10 ohm here, and then the P-channel MOSFETs tend to have a higher resistance, and that's why they're not as desirable. So let's say we have 15 ohm here, and then 15 ohm here. Now, because these two are connected in parallel, so that means the effective resistance is only half that. Because each path has 15 ohm of resistance, but you have two paths in parallel. So these two together is only 7.5 ohms. And then so if you look at the entire series, we have 10 plus 10 plus 7.5, which is 27.5 ohm of resistance. Let's assume this power supply here is 1.8 volts, okay? So now you can divide it. So 1.8 volts divided by 27.5 ohm will give you the amount of current that is passing through these resistors, which is not too much. Okay, I can do the calculation real fast and just come up with a number. I don't have BC, but that's okay. Who needs a calculator when we have a spreadsheet? Yep, totally. We can use a spreadsheet to do stuff that we normally use a calculator for. Trying to connect. There we go. Okay, get rid of this. Get rid of that. All right, so we have, what again? 1.8 divided by 27.5, which is 0.65 ampere. So we are looking at 0.065, which is 65 milliamp, okay? Which is not a whole lot. Okay, the current itself is not the bad part. The bad part is what happens when current is passing through resistance. Physics, come on. We have power, right? Okay. So VI is power, or IV is power, right? So V in this case is, okay, we can look at the whole total dissipation, okay, so that makes it easier. So we have a 1.8 volt system times the current, which is 65 milliamp. So we can do this part here. 1.8 times this one. So we have 0.117 watts, okay, which is 170 milliwatts, which is not a whole lot, okay, because if you look at these fluorescent lights, each one is 40 watts. So if each one is 40 watts, this is like 0.1 something. Let's just call that 0.1 watt. It will take 400 of these connections to make up the same power dissipation as one of these fluorescent tubes. So you would think, not a problem. Well, there's one big problem here. How big are those transistors?
Billions. Very small.
What is the size of, what is the current technology of transistor size? How many nanometers? 18. Okay, so let's call it 25. Okay, 25 nanometer. So 25 nanometer per transistor, right? I think that's just one dimension, so you have to kind of square that to get the actual area. But we are even with 4 of these transistors, and each one is 25 nanometer times 25 nanometer, which is an area. We are still talking about a very small, tiny area. Why does that matter? You're dissipating this kind of power within a very, very small area. What's going to happen?
Heat up.
It will heat up. It will heat up to what kind of level? What do you think?
70.
And warming kind of level?
No.
Boiling kind of level? Or vaporizing kind of level? We are talking about vaporizing here, okay? So what's going to happen is these transistors, depending on which one is the weaker link, they typically would be the P-channel MOSFETs. Those are usually the weaker link. So these will basically vaporize and just die. And then these would still be okay because they are the stronger transistors. So now you have permanent damage to the component of your computer. So that's usually what happens when you have a bus fight. Is that okay? Yep. So it's kind of interesting because a lot of people look at the current in the calculations and also the power in the calculation and go like, well, that's not a whole lot. Well, it's not a whole lot when you have this kind of surface area to dissipate the power, but your transistors are so small that it doesn't really have the area to dissipate the power, and as a result, the temperature rise due to this kind of power dissipating over a tiny little area is going to vaporize your transistor. It will just go away, disappear. Okay. Yep.
When you use smaller transistors like that, though, can you also reduce the amount of voltage that the entire circuit works on?
You can. I cannot remember the current supply voltage in the process, so you can look it up. It's like I5 supply voltage. So if you overclock, you have to increase the voltage, but if you don't overclock, let me see if it has any plots here. Yeah, so it looks like it is 1.26 volts, or around there is the supply voltage. So you can use a lower voltage when the transistors are smaller, but whenever you overclock, you have to bump up the voltage again. Because when you transition from a 0 to a 1, when you change the state of a transistor like this, the limiting factor is the gate has capacitance. It has a built-in capacitance. So whenever you want to change it from a 0 to a 1, you have to deal with the capacitance and drain all those electrons away in order to turn it from a 0 back into a 1. So when you have a higher supply voltage, the transition can occur faster. But the downside is power dissipation. And that's why when you overclock, you have to specify a higher voltage. But when you do that, you now need better cooling technology to take that heat away from the processor.
And if you don't raise the voltage, you're effectively causing a brownout?
Sorry?
And if you don't raise the voltage, it's effectively a brownout?
it would not be able to change the state or change it cleanly. So it would not be exactly be a brownout, but you will have your computer not being reliable because the state changes are no longer deterministic enough to work out. Okay, so we are here, and oh right, because we're demonstrating how to use a RAM module here. Okay, so this is not going to work because the same setup cannot be used to specify both a read and a write operation. Okay, but we can change this a little bit in order to make it work. So what we'll do is we're going to change the circuit, get rid of this connection here, and what we'll do is we'll also specify a 8-bit output pin, and we'll use a magic component here. So there's a magic component under gates. It is called a gated buffer, or control buffer. This is a control buffer. It doesn't look like much, does it? Okay, it looks like a triangle, but this is not a NOT gate. Why is this not a NOT gate? That's a double negation. It is a meaningful double negation.
Doesn't have a circle.
Doesn't have a circle, exactly. The negation comes from the circle itself, it's not coming from the triangle itself, okay? The triangle itself is a buffer. The bubble or the circle is what makes it a negation. So we want to turn this into an 8-bit thing because that's what we're dealing with here. And the 3 wires that are connected, this is called the gate control. In other words, it's basically specifying, are we connecting the input to the output, okay? So in some cases, we may not want to do that. And then this is the output, this is the input, okay? So now we can now specify, and we can turn it to the opposite direction and have the control line on the other side. So what we can do now is to gate it like that, okay? And then have this one connected to somewhere, and I'll let you guys, determine where we are supposed to connect it. And then this guy is just a tap, okay? In other words, the output pin is nothing more than just tapping the output of the RAM module. Whatever it is reflected. In other words, it's serving the function like a probe of the oscilloscope. Okay, it's really just reflecting what are we seeing on that wire. All right, so now I want you guys to tell me, what are we going to do with this Y here? It's going to be related to load, okay? But is it load or is it the negation of load? Because when load is 1, it is a read operation. And when it's a read operation, we do not want the buffer to drive this line. So we want the negation of the load, okay? So we'll go ahead and use a NOT gate here and just negate the load signal and use it to control the gated buffer. So now we can specify a read operation, no problem, okay? This is a read operation, and the location has a content of B5, which is reflected here as B5. So the input pin is having a different content, but because this buffer is acting like a clutch, okay? It is separating the input from the output at this point, so we don't have a bus fight anymore. Is that okay? All right. So what if we want to specify a write operation and we want to change this location here, 0D, location 0D, to the content of 78? What do we need to do? Okay. Yeah, we need to change the address, but before you do anything to the RAM module, it's a good idea to deselect it first. In other words, you're telling the RAM module and say, don't pay any attention until I have everything else set up, then pay attention. Okay, so it's good to turn off the select pin. Then you can go ahead and specify, oh, this is going to be a write operation, and then the location we want to write to is this one, which is 0D, and 0D is 1101. The most significant 4 bits would still be 0 because it's a 0D, and the content we want to write into that location is 78, which is already specified here. Now we are ready to say, okay, RAM chip, you can now pay attention because we got everything else specified. So you can see that location is now quote-unquote addressed because it's highlighted, but it is not changing, okay? Okay, let's check out everything. This wire is reporting 78, which means the D port of RAM is reading 78. This is 0D, and we can see that 0D, the location 0D, is being addressed because it is highlighted. So why is it not changing? The clock, exactly, because we need a rising edge in order to write something. Just like with registers, we need a rising edge to specify, now go ahead and change the location. So we track down the clock line here and say, okay, let's go ahead and specify a rising edge, click, and now the content changes to 78. And because it's a clock signal, it will eventually go back to 0. When the operation is done, we want to deselect the RAM and basically say, okay, now it's done, do not pay attention anymore. So is this okay? Because everybody understands the basic operation of a RAM module. Is that okay? Cool. All right. All right. So that's a RAM module. And then the next component, you can see how it has a lot of control wires and you have to set up things, and it is relatively slow. Okay. Why do you think your RAM is slow on a PC? Even though you have the top end, like EDR, 4 gazillion, it is still slow. Why is it slow?
Because it has distance.
Go ahead.
I was gonna take a guess, because there's distance between the RAM and the chip.
There's distance between RAM and the processor, which is eventually going to consume the content supplied by RAM. Why would that be a difference? Why would that make any difference? In other words, you have your processor chip here, right, which has the ALU, which usually is represented by a funnel, and then it has its own registers like that, which are really fast to access. And then on the other side, you have your RAM chips, which is usually in its own module. What is the name of the RAM modules? DIMM, D-I-M-M, for dual inline memory module. Or if you have a laptop computer, what is that called? SODIMM, because it is small outline DIMM. Okay, very good. So they're kind of further apart. If you ask any software person, a software person will say, well, logically they are connected, so it should not make any difference. Because that's what software people do. They look at things from the logic perspective and not take physics into consideration. But when you ask a electrical engineer, the electrical engineer will say, oh, no, this makes a big difference. Why would they make a big difference? Why would this wire, this conductor, make a big difference?
Distance.
But why would that distance make a difference? As capacitance? Okay, very good. So there's an inherent capacitor involved in here. Okay. What else is here, which is even more significant?
Is there a voltage drop?
There's a voltage drop because of a minor resistance, but that's not the reason why it is going to be slow. Inductance, very good. Okay. So there's an inductance here. This is the representation of an inductor on the wire. Okay. Inductance is kind of nasty and also really cool at the same time, depending on whether it is on your side or not. When it is on your side, it's really cool because this is why we have light and power efficient transformers. Okay, just look at your USB transformer. Okay, the wart thing you plug it into an outlet so you can get your 2, 3 amp or 5 volts to charge your phone and stuff like that. And you compare that to a transformer that your dad used to have for his electronic stuff. Okay, you weigh it. What do you feel? It's a lot lighter, right? The ones that we use today are a whole lot lighter. And then you plug it in without actually any load. What's going to happen to the new transformer? Does it heat up with no load? Nope, barely heat up. If you have a FLIR or one of those thermal imager, you may be able to tell that it is connected, but you cannot feel any warmth coming out of it. With the older transformer technology, the moment you plug it in without any load, it's gonna warm up. Okay, and it's heavy because it is using a very old technology to transform the voltage from a high voltage to a low one. Inductance is what allows us to use the current high efficiency transformers. Okay, those are called DC. What is the name? No, I cannot remember the name of those transformers, but they are very efficient. It's based on inductance. But in this case, inductance is not your friend. Okay, what is the closest analogy of inductance in electrical circuits to something in Newtonian physics? Momentum, okay, pretty close. It's like a flywheel. Okay, so it's like a flywheel, which basically means if you want to drive current from on this wire, this is a flywheel. Okay, you cannot just start turning it. Okay, it has to ramp up. So it takes time to ramp up, and once you want to turn it off, it cannot just turn off. You have to apply the brakes and then wait for it to slow down to a zero. So inductance is indeed a problem because it will turn a signal that looks like this, which is ideal. This is what software people see on that wire. And then electrical engineers will see something that's completely different, okay? Because of inductance, there's no way you can change the voltage instantaneously. Because in order to change the voltage instantaneously, the amount of current change is also the derivative of current change over time is infinite. That's not possible with an inductor. So with the inductor, you can only ramp it up very slowly, okay? Like that, okay? And when it's time to turn it off, what's gonna happen? The inductor says, we're not gonna turn off this current right away. So the inductor would keep the current going, even though this side says, no, we want to turn it off. So it would get a dip like this. It would dip below zero because of inductance, and then it will have a spike back to here. And this is actually if you use a oscilloscope and look at a high-speed signal on a digital line, you should be seeing this, okay? But you will see this instead. It's a shark fin. This is why when you have two components on the circuit board and they are spaced out by a sizable trace, you cannot have those two to communicate at a high speed anymore. Is that okay so far? I'm not going to ask any questions about this, but I do think that this is kind of important. If you just remember, the inductance of a wire is partially why we cannot change the signal instantaneously, that's good. Okay, just having that understanding is actually beneficial. Because I don't really want software people to go out to the real world and say that it's just a wire, logically they're connected. Well, it's not just connected because of physical characteristics. All right, so RAM is slow, but registers are fast because they're on the same chip right next to the ALU. Okay, so the next thing we want to do is to say, so now that we know registers are great because they are fast, how many registers do I want? Well, minimally, how many do you think we need? 3 would be good, but there are processors out there with only one single register. Okay, so we can take a look at ancient architectures, just so that we know, okay, how did we get to the current type of architecture? So if you go look back in time, look up 6502, which is a processor used in the original Apple II computers. This is kind of interesting. My ADD is functioning just perfectly because right now I am being reminded of Steve Wozniak, and then I'm remembering his dancing with. What is that? The name of the show? They invite these celebrities and they dance. Dancing with the Stars.
Yeah.
Okay. So Steve Wozniak actually was in 2 or 3 of those competitions. It's fun to watch. Okay. He is the opposite of what you would imagine to be a contestant in those competitions. But he was brave, he said, I want to give it a try, and he did okay. And the judges even gave him enough score to keep him around for like 2 more rounds. And then he made some stupid comments about, I think the judges nudges my score to keep me around, and of course then he got drunk. But it was interesting. He was doing tango and doing all kinds of high difficulty moves and whatnot. And his partner, when they first met at the dance studio, his partner looked at him and go like, we have a lot of work to do. That was her exact comment. So anyway, that's my ADD working. It's just branching out and connecting all the things that are irrelevant to the class. But sometimes good stuff comes out of that also. So anyway, this is the 6502, and if you look at the architecture and particularly go to the registers, it has got some really kind of interesting setup. It has one single 8-bit register and then 2 index registers, which are special purpose. And it has a stack pointer, which is also 8-bit wide, program counter, which is 16-bit wide. We are going to deal with all of these registers, except we don't have special purpose registers except for the program counter. So all of these are kind of useful. And then look at the status bit register. Okay, look at this IP register, processor status flag bits. Okay, how do you think that relates to this class up to this point? Yep.
Didn't we talk about flags earlier?
Yep, those are the flags. So that is the representation, or out of the 7 bits, it would include at least 3 of the 4 bits that we talked about. Possibly the 4 bits, except not for the L bit, because the L bit is actually an artificial bit that I created for convenience. But it will have the other 4 bits, which will be the carry flag, the 0 flag, the sign flag, and the overflow flag. Okay, so we are now starting pretty close to actual architectures. Okay, but it only has one single accumulator, which is used for calculation, and then the index registers are only used for memory access for indexing purposes. The stack register, the stack pointer is only for stack operation. We'll talk about that later as well. But this is kind of like a minimalist processor by today's standard. So for our toy processor that we'll be using in this semester, I'm going to say we will need like 8 registers. Okay, so let's go ahead and take a look at what it will look like if I need to have 8 registers. So we go to memory, and we pick out registers, a single register, and it's pretty easy to get 8 of these things. Okay, because we just have to do something like that, right? Okay, Control Z, and now we have 8 registers. Oops. Control Z one too many times. Can we redo? Undo. Okay, there's no redo. Fine. Okay. I lied because the processor that we're going to use only has 4 registers, but there will be an explanation today why there are only 4 registers. Okay, but let's say there are 4 registers. The register bank has to feed to the ALU. How many inputs do we need at the ALU, the arithmetic and logic unit? It needs 2, right? So now the question is, which 2 of these processors do we want to connect to the ALU? And which one are we going to use to store the result of the calculation? So those are the questions that we have to answer. What if we have a larger architecture and we want to specify that we want to use 8 registers? Why do we want to have more registers from the perspective of the compiler? Why would it be faster? You're correct. It is going to be faster because we have more registers. But why do you think more registers will help the compiler to translate code into something that is more efficient? When you look at a typical program, okay, so when you look at a loop, there's usually a particular variable used to control the indexing of the loop or just counting something in the loop, right? If that can be stored in a register and not to put back into RAM, that will increase the efficiency of your program, wouldn't it? Okay? But what if this is a loop inside another loop? So the outer loop has its own control variable, and then the inner loop has its own control variable, right? And then the loop itself probably is doing some kind of calculation, okay? And the calculation may have a value that is useful for a few iterations. So the key is, you want to store as much, you want to put as many variables into the registers as you possibly can, because anything that is stored inside the register is really quick to access. But if you run out of registers, then you have no choice but to store those variables in RAM, which is going to be slow. Is that making any sense? So that means the more register you have, then the compiler can decide, oh, I can put this into a register, I can put that into register, and so on. And when you have most of the variables in a tight loop in registers, the program is going to run a whole lot faster because it doesn't have to go out to RAM to deal with this problem. So that's why more registers gives your compiler the room that it needs in order to crank out more efficient code. Yes?
So how does it choose what's the most important variable? Just by use?
It is by the analysis of the flow of your program. So when you get into a compiler class in a 4-year university, they might talk about optimization a little bit, but basically a compiler has a component that is called an optimizer. And what it does is it will analyze your control flow, your conditional statements, your loops and stuff like that, and it will look at the expressions that you use in your program. And it will try to figure out, okay, if you are computing this thing and you're storing this into a variable, are you reusing that variable without changing it throughout your code? If you are, then it makes sense to put that variable into a register, because now getting back to it is like quick, right? On the other hand, if you have a variable, you put something into it, but you only use it at the very end of the subroutine, then you put it back into RAM because we're not going to use it anytime soon. Does that make any sense? So your compiler has the capability of analyzing the flow of the logic of the program, and if it can figure out that a particular variable is used frequently and the same value is a lot of read operation without changing it, then it will try to use a register to store that variable. It's all done automatically. You really cannot control that part of your compiler. You can make a suggestion, use the register keyword as a suggestion, but you can never really tell it which one needs to be stored in a register. So the bottom line is the more register, the better. Okay? And that's why most of the RISC processor today, they have a lot more registers than like 4. Okay? Because they are much more compiler friendly in that respect. Okay. So for reference to that one, you can look up the ARM architecture. Yep.
Is it necessary to have like different registers there, or can you have kind of one register that can store, like let's say you wanted to store 4-bit numbers, you could have an 8-bit register store 2 4-bit numbers.
Okay, so dividing a register into multiple parts typically does not work out very well, because there are no quick way to address a particular part of a register. In other words, there's no single instruction and say, oh, I only want the most significant 4 bits of this 8-bit register or the other 4 bits. So to get to the 4 bits that you need to access, a lot of times you have to rely on bitwise operation, to use a bitwise AND to mask out the portion that you do not want to use. And then you have to use a shift operation to shift it back into the position where you want it. So you actually end up wasting a lot of time by trying to partition a single register into multiple parts. And that's why when you deal with a 32-bit architecture, which typically has 32-bit registers, and you want to store a char in a C program, it would take up one whole register. It's not going to combine the storing of 4 individual char variables into one single 32-bit register, because it cannot address individual parts of the register, not quickly.
How does RAM handle addressing variables?
Same way, your RAM, okay, let me go back to the RAM here. But before we do that, I'll just take a quick detour to the ARM architecture, because with the ARM architecture, the number of registers is actually quite a bit more than the 8086 architecture. So when you look at registers, it has 12 general purpose registers, and some of these are kind of not so general purpose. But you do have at least 8 completely general purpose registers, and then 5 more that are sort of general purpose, which means they can be used in any instructions. Getting to your question, what was it again?
Oh, I'm curious, since you said that like bitwising registers is non-effective.
Right.
How
Okay.
does RAM have multiple
So RAM is just as inefficient. Okay. Let's get back to this point here. So this is a very simple RAM module where each location is only 1 byte wide. Okay. Now with all the computers that we use today, they are all called byte addressable. In other words, each byte in memory has its own address, And that's why in C++ or C programming, you can have a char pointer, and then when the char pointer is increased by exactly 1, then you can get to the next char or the next byte. Okay? But when you access memory, it is always accessing memory by not only 1 byte, it's always accessing by 64-bit or even 128-bit wide. So when you say, when in your code you say, okay, I just need to get that 1 byte, the computer would actually go through the motion to grab 8 bytes or 16 bytes. Because you cannot get any less than 16 bytes at a time. The width of your memory bus is 16-byte wide. So if only one of those is the byte that you need to access, the other 15 bytes will still go through the transaction. It will just be gated at the memory management unit, so it's not really fed into the processor itself. But as far as bus operation is concerned, they all go through the D bus, the data bus. Is that answering your question?
Yeah.
Yep. So now, so when you look at a byte or char pointer dereference now, you will start to look at it kind of differently, because it is not really that, is in no way more efficient than dereferencing a 32-bit integer. It's just as bad. All right, so getting back to the registers, there we go. So now we have 4 registers. So what we need to do is to have 2 outputs out of this entire register bank, because now we want to say, we want to be able to use any one of these 4 as the first output, any one of these 4 as the second output. So how do we do that? We already talked about a particular mechanism that can do that.
The mixer or the muxer?
Is either mux or debux, right? Okay, so let's go figure out which one we need. So they're all called plexers. So this is a mux, this is a demux. From the shape, which one do you think we need? We need a demux to control the, no, we need a multiplexer, sorry. We need a multiplexer to control the output. So a multiplexer looks like this, okay, by default, and there are things that we can change. By default, it only has one single select bit, and the select bit is what is selecting one of the 2 inputs to become the output. Well, we got 4 inputs in this case, so what do we need to do? We need to change the select bits to 2. Okay, very good. So once you change it to 2, you can see that the mux immediately changes to reflect that now we have 4 input ports, and then this is now a 2-bit thing. This one is enable, which basically means, if it is a 0, the output is not connected to any of the input. If it is a 1, then the output is connected to one of the inputs based on the select. Are we okay so far with the operation of a mux? Okay. So what we need to do is to say, okay, this is the first output. Okay, so we draw this line. This is the first output, and each individual register will feed one of, I'll fix the width a little bit later. Okay. So each of the register is going to feed into one of the inputs. And the fixing is easy. We just have to change the number of data bits from 1 to 8, and that will fix the width in discrepancy. And then we have to control the output enable. Okay, so this is a wire that we have to deal with. And to control the second output out of the entire register bank, we can do exactly the same thing. So we'll just go ahead and replicate this one. And the interesting thing is, we are really just replicating all of these control signals over to this one. Okay, I might need to do something. It'll work. Just doesn't look very good. There we go. Okay, so now we have 4 registers, of which we can select any one of these 4 as the top mux output, and any one of these 4 as the bottom mux output. If we want to, we can select the same register to be both. Okay, to feed to the both the upper mux and the lower mux. All right, cool. All right, so after this, we need to look at the input, right? So this is the output. Now we need to look at the input. So the input basically has one single thing, and we want to say, okay, which register do we want to update? And this time we need a demux, okay? Now that's one way to do it, but that's a different way to do it. A demux is kind of expensive, so one way to do it is to connect all of these Ds to one single wire. Okay, so let's hook up all of these guys to the same wire. Okay, that doesn't look very good, does it? Because now we are saying, oh, any one of these, we have one single line coming in to specify the content or how to update the register, but it is the same wire going into every single register. How do we fix this problem? We don't need a splitter, but look at the other pins. Look at the other pins on the register and tell me which one is going to be useful here. Enable, which is the same thing as select. Okay, so the enable pin of a register is serving the same purpose as the select pin of RAM and ROM. Okay. So now what we need to do. Okay, I did not leave myself enough room to do it. So let me see if I can kind of hack it. Because I need the space to specify a few more wires. Okay, 3. Okay, we got enough. Okay, there we go. I think we're good now. So what we need to do is a decoder in this case. And once again, we need 2 select bits because a decoder is kind of like a special demux where the input is always a 1. Okay, and that's why you don't see a pin coming into a decoder because it's always assumed to be a 1. So now, out of the 4 outputs, we'll just have one output going to, we can do this. It just looks ugly. There we go. So this goes to the first one, this goes to the second one. Oops, that's not what I want. This one goes to the second one. There we go. This one goes to the third one. And this one goes to the last one. Just barely have enough room to route it. There we go. Okay. So the decoder has 2 pins right here to control which one of the output is a 1. So once again, we can now select one out of the 4 registers to be the one to be changed. Because the enable of only one out of the 4 is going to be a 1. Is that making any sense? But we can consolidate all the Ds, okay, 1, 2, 3, 4, and just connect everything to one single common wire, which has its own input pin. Are we doing okay so far with this picture? So now we have a way to specify which one out of the 4 registers we want to update, and we can only update one register at a time. But we can specify any one of the 4 to be the top output, and any one out of the 4 as the bottom output, because we need 2 outputs to specify the inputs into the ALU. Are we doing okay so far with this? Okay. So what is left to do here is to basically hook up the input pins so that we actually have something connected to all of these things. So this input pin is going to be 8-bit wide, and it's going to have a name of register input. This is the content of the register input. This line here needs to connect to, it needs to select which register are we updating. So the pin that I'm going to connect to it is going to have a label to reflect that. It's going to be 2-bit wide, and then the label is register in select, which basically means these 2 bits allow us to select which register do we want to change. This 1-bit wire, we know this is a 1-bit wire because it is blue in color. This one, we'll call that register in enable, which basically just means, are we changing anything? Because I can select this to be a 0 and basically say, we are not changing any one of these registers. Is that okay? And then on the output side, basically the same thing. It's just a nomenclature kind of thing at this point. So we have the output pin, 8-bit wide, and we'll call this one register output 0, and then we'll call the other one register output 1. You don't have to really copy this because these are all in one of the files that is in the share drive. So there's no need to copy this. Okay. So now we have register output 0, register output 1, and these pins are now just used to control whether we want that to be an output or not, and which one we are selecting. So we'll bring out these wires and change the direction, and then change this name. This is going to be register out 0 select, because we are selecting which register is going to be, Control Z, change the E to lowercase, there we go. And make a connection here, make it 2-bit wide, and we'll duplicate this. This becomes register output 1, select, and then we just have 2 enables to deal with, and we are basically done with the register bank. And we still need to change the to best. And this will be register out 0 enable. Do we need an output from the top mux? And then this one is the other one. And we call this register out 1 enable. That's it. This is our register bank. So the interface to the register bank will consist of the data ports, 1 for updating registers, 2 for outputting or pulling, reading the registers. It will have the control lines, all the enables, because if we don't really need to do anything with the registers, we can disable the registers. So that would help save us some power. And then we also have the select lines, which basically means, okay, we need to update one of the registers. Which one are we updating? The select lines is for us to select which register do we want to use. So are we doing okay so far with this picture? Okay, so functionally this is called the register bank, which is very, very useful. Okay. And as I said a little bit earlier, there's no need to copy this because it is already on the shared drive. So when you go to the shared drive, okay, let me see if I can quickly locate the shared drive. So go to cisp310, go to shared, go to processor, and regbank, register bank, is the file that I'm talking about. So this file, is a Logisim generic file. So if you don't want to use Revolution to open this, just use the generic version, and it'll give you the register bank. The signal names may be slightly different because I might have done some tweaking to make it work with the processor, but the idea is the same. And since we do have a little bit of time, let me just go ahead and download it. And I have it downloaded already, I just need to open it. So let me go ahead and open it. So it is in downloads, processor, there, and register bank. There we go. So it's exactly the same as what we saw a little bit earlier, except it also has the clock and the reset signal. So those are external signals, which basically means when the reset line is held, all these registers will reset to 0, which is a save no state again. The clock is also distributed to everything. So you can see how the clock line over here, let me see if I can scroll up a little bit. Okay, maybe not. So you can see the clock line is also shared by all the registers. The reset line is shared by all the registers. The input D line is shared by all the registers. The only lines that are not shared are the enable line, one for each register. And then for output purposes, each register is connected to 2 inputs of the 1 input to each mux, so that we can select which one is actually going to be the output. So this is a register bank. So getting back to the earlier question that I asked myself, why are we limiting our processor to only 4 registers instead of 8 or 16 and stuff like that? Okay. It has to do with the width of instructions. It is good to have instructions pretty much as wide as everything else. Okay, so if we have 8-bit registers, 8-bit ALU, we also want our instructions to be 8-bit wide. So we have 8 individual bits to specify an operation. Question?
Is that why like certain programs are optimized for 32 to 64-bit and it doesn't work across?
Sort of, because when you switch from 32 to 64-bit, the number of registers available is also changed. So the AMD 64-bit architecture actually has an expanded set of registers. Okay, so in our particular case, in this particular toy processor, we have 8 bits to specify a instruction. So let's say we want to specify an add instruction. What do we need to specify in order to use the add function of the ALU? Minimum, at the minimum, what do we need to specify? When you perform an addition, what do you need? Which 2 things are we adding? Okay, very good. Which 2 things are we adding? So because this is a RISC processor, we can only use registers as the operands of the addition. Okay? If I have 16 registers, how many bits do I need to specify a register out of 16? 4 bits, right? Because 2 to the power of 4 is 16. Well, that means I would use up all 8 bits just to specify which 2 registers I need for an add instruction. Where's the part to specify this is an add and not a subtract instruction? I cannot fit into 8 bits anymore. Okay? If I have 8 registers, I will need 3 bits to specify 1 register, which only leaves me with 2 bits to specify which operation I'm going to perform. And that doesn't give me enough room for all the instructions that I need to implement. So I really have no choice, okay? Given that this is an 8-bit architecture and the instructions are only 8-bit wide, I really have no choice than to say, okay, we can only dedicate 2 bits to specify one of the 2 things that we're adding, and then use 2 more bits to specify the other thing that we're adding. And then we can make the assumption that one of these 2 will also store the result of the addition. That will save me the other 2 bits. So now we have a lot more bits to play with in order to specify what are we doing with these registers. Okay, we use one particular pattern here to specify this is an add, another pattern to specify this is a subtraction, another pattern to specify this is a bit shift operation, bitwise AND, bitwise OR, and so on. And this is why I'm limiting myself to only using 4 registers. It has to do with the width of the instruction itself, and I want this to be only 8-bit wide because memory location is only 8-bit wide for each location for the toy processor. Okay, so this is the rationale why I only select 2 bits to specify 1 out of 4 registers. Is that okay? All right. So we are running out of time. In case you are not done with your homework assignment, we can continue to do that at the lab. If you have any questions about any topic that we talked about today, we can talk about it at the lab as well. Otherwise, just remember to turn in your homework assignment on Thursday before class. And then on Thursday, we'll probably end up with a new homework assignment that will combine all of these things that we have just talked about.